In this video, I'm going to demonstrate the usefulness of physics, and we're going to have a brief introduction into science in general. This will start to cover the material from Chapter 1 of your textbook. Let's start with the question of what is physics. I could give you a generic definition, but I thought it would be more interesting to go through a demonstration instead. Here I'm showing two cylindrical objects, a ring and a solid disk. These objects share a few traits in common. The first is that they have the same diameter, so they were manufactured especially for our purposes today. The second characteristic is they have the same, or roughly the same mass. So you may wonder, how can an open ring have the same mass, or you could say the same weight as a solid disk? Well, the ring is made of metal and the disk is made of wood, so the high density of the metal compensates for the lower volume. Here's just another picture so you can see the similarities. Alright, so what we're going to do with these two cylinders is we're going to race them down a ramp. I'll remove the wooden block and we'll just let them roll down at their own pace. What I'd like you to do is think about the properties of the disks and decide which object will win the race. Okay, before you commit too much to one of the objects, just remember they have the same mass and the same diameter. Think about that and see if it changes your decision. Okay, now I want you to go ahead and make a firm commitment. We've got three choices. Either the ring's going to win, the solid disk, or of course it could be a tie. So pick one of those and commit to it right now. Okay, the best way to test this out is just to let them roll, and so we're going to watch and see what happens. Okay, so we had a clear winner. It was the solid disk. Physics is a science, and an important issue in science is the question of reproducibility. So before we can be confident that the solid disk is going to win every time, we need to test if this is a reproducible result. The best way to do that is just simply repeat the experiment. Each time we're going to call it a trial. So the more trials we get, the more data we collect. More data will allow us to make some statement as to the significance of our result. Alright, now we have three data points that state the solid disk is the winner every time. 3 data points isn't necessarily good statistics, but it's better than 1. Another issue we should address as good scientists is the possibility for other explanations. We could spend a while doing this, but we're just going to focus on one. And I think this one's pretty obvious. What if it was just the starting position? What if there was something about that far position for the solid disk that gave it an advantage over the closer position for the ring? So to test that, we're just going to do more trials, collect more data. Watch this time, I'm going to swap their starting position. Okay, so now we have 5 separate data points, and we've considered at least one other factor that could have been influencing the results, and all of those has shown us the solid disk is the winner each time. Here's where physics comes in. Why did the solid disk actually win? The fact that they had the same mass and the same diameter made it so both cylinders experience the same force and torque. If you don't know much about force and torque, don't worry, we're going to talk a lot about those this semester, so you'll be familiar with those by the end. When I look at this observation, it actually makes me think that there should have been a tie. If they had the same force and the same torque, wouldn't they roll down in the same way, and so they would tie at the bottom? Well, the missing piece to this question is a concept known as rotational inertia. The solid disk had less rotational inertia than the ring. If you're not familiar with the concept of rotational inertia, don't worry about it. We'll discuss it later in the semester. Here's a preview. Rotational inertia is a measure of an object's resistance to change in rotation. So maybe I could say it another way. Since the solid disk has less rotational inertia, it's easier to rotate the solid disk. There's less resistance to that change in rotation. So if both cylinders are experiencing the same force, the one that's easier to change rotation will start to rotate faster, and that's what's happening as they race down the hill. They're changing their rotation or speeding up, so the solid disk is the winner. You could make a comparison with the concept of inertia, not rotational inertia, just inertia. Inertia is a measure of an object's resistance to change in motion. It's connected to the idea of acceleration. So if you take a small rock that has small inertia and you apply a small force, you can still actually change the motion of the rock fairly easily. But if you take that same small force and apply it to a large rock, which has large inertia, you'll get much less effect or much less change on its motion. So rotational inertia is really the same thing. It just applies to the rotation rather than the motion. Now, if we had this knowledge before we started our experiment, then we could have easily predicted the winner of the race. So this is an example of why physics is useful, and hopefully give you an idea of how we're going to use it. We still haven't exactly addressed this question. What is physics? I decided not to go with a dictionary definition here. You can go ahead and look it up. It'll say things about matter and energy and all that stuff. But to me, this is how I like to think of it. Physics is simply the science of how things work. I love knowing how things work, so I get really passionate about physics. I'm hoping I can spread some of that interest and some of that passion to you guys during this semester. If physics is a science, then that brings us to another question. What exactly is science? Do me a favor. I'm going to pause for a few seconds. Try to answer this question for yourself. I'm sure there's multiple definitions we could give, but I like a simpler one. I'm going to go with, it's a common approach to explaining the world around us. When I ask this question in class, students often start explaining this, the scientific method. While this isn't exactly the answer to the question, it is something familiar and it's something most of us have covered in earlier science courses, so we should at least go through it. It starts with, of course, recognizing a question. Once you have your question, you make a hypothesis, and what that means is you propose an explanation based on limited evidence. Next, you'll predict consequences of your hypothesis. And what that means is you would ask yourself statements like this. If I do this, then that should happen. Once you've worked out those statements, you perform experiments to test the hypothesis. And then when you're done with that, you repeat until you arrive at a general rule that can be agreed upon. So that's probably familiar to you from your previous experiences in science classes. As an example, we actually did follow this process when we were going through our physics race earlier in the video. I hope you're reading your textbook. I've assigned it because I really do think it will help you in this course. It's good to have a second opinion, a second viewpoint of the material. As I was reading the textbook myself, there was a few quotes that I really enjoyed as far relating to science, and so I wanted to go through those. The first was, "The science attitude is one of inquiry, integrity, and humility. That is, willingness to admit error." At its core, this is what science really is to me. Now, I'll admit that I've met plenty of scientists that aren't very willing to admit error, but the basis of science is this idea that you all work together to achieve the best results, and so that requires, of course, all of these traits. The second quote is that progress is full of trial and error. Plenty of important discoveries were just accidents, but someone happened to be paying close attention. I really like this quote, especially for our course, because at times it's going to seem like we're going to cover basic, pretty obvious concepts, and you're wondering why we're spending the time on it. But remember that it's these basic observations and understandings that usually lead to big discoveries, to big new discoveries. So it's important to build this knowledge base. Now we're going to go over some science terminology. We've already discussed hypothesis. Let's bring in a new concept, a law. So what's the difference between hypothesis and law? In this class, we're going to discuss Newton's laws of motions quite a bit. So here's a good example of a law. So the question I have is, when does a hypothesis become a law? Do me a favor again. I'll give you a few seconds. Try to come up with your own explanation. Okay, let's see how you did. A hypothesis becomes a law after it's been tested over and over again with no contradictions. Newton's laws, for example, have been tested for centuries and they always seem to work, so we call them laws. Next term, scientific theory. To answer this question, I'm going to ask you a question. Read through these options and choose the one you think best answers the question. If I can get on my soapbox for a minute, I really hope you're participating with me in these videos. There's a couple reasons why I want you to do this. First of all, it's going to be really boring if you just sit and listen and don't really participate. So do yourself a favor, try to make it a little better experience, and join with me on these questions. The second reason is it's proven that if you don't actively think about the material, you're unlikely to retain any of the knowledge. So if you really are interested in learning, or if you just want a good grade, do yourself a favor, participate with me, and I think it'll make this time much more enjoyable. Okay, I'll get off my soapbox and let you answer the question. Okay, the most popular choice is usually this one right here, an idea of something that has not yet been proven. That makes sense to me because this is how we often use the word theory in everyday conversation. It's something that is just developing and we're not really sure, and so we just call it a theory. However, in this class, we're discussing scientific theory. It's not necessarily the same as just theory in general. In science, a theory is supposed to be a large collection of information that encompasses well-tested and verified hypotheses. Okay, the key is really this idea of a large collection. So when you have a lot of information that you can put together and create some sort of an umbrella, an overlying concept. That's when we call it a scientific theory. But that is well tested and verified. So a lot of effort is spent in really having confidence in this result. Okay, now I will mention that in general theories are more open to evolving as new evidence arrives, because it's a large collection. So there's a lot of little details that can be added to change the overall structure of the theory. But it's not as wishy-washy as people like to use it. So for example, theory of evolution or a theory of relativity. These things have a lot of science that's put into them, a lot of confidence in the results. It's just a large collection, so we call it a theory. Before we end our introduction to science, we've talked about what a hypothesis is, but we should discuss what is a good scientific hypothesis. So as I usually do, we'll address that with our own question. Take a minute and pick which of these two options you think represents the best scientific hypothesis. All right, before I answer, take another look at it and really think about it from a scientific standpoint. When I ask this in class, the popular answer is usually this one. Intelligent life exists on other planets somewhere in the universe. That does make sense to me. It's certainly the most optimistic choice. It seems like something a scientist would say. But there's an issue that we need to consider. A hypothesis that is capable of being proven right, but not capable of being proven wrong, is not science. Okay, so let's go through both of these options with this in mind. So let's start with B. Intelligent life exists on other planets somewhere in the universe. Well, this is relatively easy to prove right. We just need we just need our first interaction with intelligent life from somewhere other than Earth. That could happen because they came to us or we came to them. So that's why it seems an optimistic choice. But here's the issue. We need to be able to prove it wrong. So how are we going to prove this wrong? Well, let's say we spend the next 1,000 years exploring all the planets that are around us, and we don't find intelligent life. Well, we haven't proven this right, and we haven't proven it wrong. The big issue with this, though, is space is really large. So in 1,000 years, we wouldn't make a scratch in terms of exploring the total volume of space. The only way you could prove this wrong is if you have absolutely covered every square inch of the universe and you've absolutely not found any life. That's not going to happen. It's just not. And so there's really no way to ever prove this one wrong. So that's why B is actually not a good scientific hypothesis. Let's look at A. There is no other intelligent life in the universe. How do we prove this wrong? Well, we run into at least one other form of intelligent life in the universe. In terms of the previous option, that's actually pretty easy to prove wrong. Okay, so that's why A is actually the better scientific hypothesis in this case. So I'm going to end with this statement. Perhaps what characterizes science the most is that everything must be testable. You need to have a way to prove it wrong. If you can prove it wrong, but after many tests it's not proven wrong, that's when you gain confidence, and that's when you're doing science. That's all I have for this video. I hope you enjoyed it.